Welcome to the Organic Chemistry Coronavirus Bunker in Portland, Oregon. So this is SLO6 video 1, where we'll be introducing the Grignard reaction. So we're going to take a trip back in time to 1901, and we're going to be looking at an experiment performed by a Frenchman named Francois Grignard. So Americans call him Grignard because we mispronounce everything. And what he did was actually pretty simple. This is actually back in time when you could mix random shit together and become famous. In fact, Grignard won a Nobel Prize for this work. And what he did was actually took this ketone, which has an alkene functional group as well, and mixed it with a magnesium metal. Right? So it's important that we think about this as just metal like what you'd see in a pipe or in a flare. I'm going to write a 0 over the Mg because that's its oxidation state in this reaction, at least initially. And then also iodomethane, so a methyl group with an iodine attached. So Grignard mixed these together, presumably went for, whatever coffee, wine, whatever French people did in 1901, came back, added some water. This is probably sounding a little bit familiar, like a workup, right? And what he actually was able to identify was that the ketone functional group had disappeared, and instead he isolated this kind of a product. And then subsequent work also showed that he was forming magnesium salts that have a combination of different anions, right? So this would in this case be a mixture of I- and hydroxide anion. Right, so just to get us started, what I'd like for you to do, just quickly in your notebook or in some scratch paper, I want you to execute a bond accounting here. So which bonds are breaking and which bonds are forming. I would also like for you to evaluate the oxidation state of magnesium in the reactants, so that would be this species here, as well as in the products. All right, so go ahead and pause the video, and then once you've actually written out your bond accounting, you can press play or resume, and we'll pick up lecture there. No, seriously, pause your video. Bond accounting. Okay, so you've done your bond accounting now. I'm going to go ahead and do it as well so that you can check your work. So what I'm observing is that the ketone CO pi bond appears to be disappearing. So our bond counting minus CO pi. I'm also not observing a carbon-iodine single bond anymore. So minus a Ci sigma bond. It seems to me like I'm making an OH bond here. So this oxygen didn't have an H before. And it also looks like I'm making a carbon-carbon bond, which is interesting. I don't think we've actually seen reactions that look like this yet, right? So I'm just going to highlight that bond in red so we can be really clear about what we're describing. So we've got a new CC sigma bond. And I think there's two other things that we need to find here. We're breaking, presumably, an OH bond from the water molecule. All right, and so I think that is everything. Cool. So these are the set of structural changes. And then I also wanted you to think about oxidation states of magnesium, right? So we've already established that this is at the +0 state. All right, so it's just a metal. And if I look at the magnesium in the products here, I see that I've got I- and OH-. If this is all together as an ionic compound, that magnesium is going to be at the +2 oxidation state. So we see that magnesium is actually oxidized here. But that means that something had to be reduced. Right, so if you look carefully at this, and in particular, you note that we're actually breaking a CO pi bond to make a CC sigma bond, right? Then basically what we're describing is reduction of carbon, right? So this carbon here would be at the +2 level, right? Remember, these aren't oxidation states. This would be like the +2 oxidation level of carbon. If I find that same carbon in the starting or in the products, excuse me, I'm seeing that I've now made it into the +1 level, so a ketone to a tertiary alcohol. So our carbonyl carbon is reduced. So this is just like borohydride reductions or lithium aluminum hydride reductions of carbonyls, but instead of making a CH bond, it looks like we're making a CC bond, right? So we can say analogy to hydride reductions. That might be helpful for us because we don't have to treat these reactions as fundamentally new. We already kind of understand them. What we basically changed is the group that we are adding to the carbonyl carbon. So rather than a hydrogen, we're adding a carbon of some kind, right? Okay, so we've done our bond accounting, we've done our oxidation and reduction analysis. What I'd like to do to finish up this part of our conversation when we're first encountering the Grignard reaction is to actually briefly think about how the CC bond must be forming. So nature of, that'll happen a few times. Nature of CC bond formation. So in particular, I want to think about roles. So in my carbonyl carbon, right, so what we've annotated here, we would typically think of these as electrophilic sites, yeah? So we've labeled these in the past with like E plus or E, and then we can think about where that same carbon would be in the products. It's here, right? So when I think about this new bond forming, I now can infer that this carbon must have been the nucleophile when this reaction occurred. That's the only way that I can make sense from like an electrostatic or a mechanistic perspective of how this reaction is happening. So just like we invoked H- or something like H- for a borohydride reduction, we would need to be thinking about carbon-based nucleophiles. So our incoming carbon group is nucleophilic. Or maybe it would be better to say was nucleophilic. In the products, this carbon is no longer nucleophilic. What we're thinking about is the bond that I'm showing in red actually forming. In that case, this carbon group was the nucleophile, right? Okay, so Grignard thought about this in a similar way. Other kinds of carbonyl reactions involving nucleophiles were already known. And so what he also did was a control experiment. So Grignard thought that maybe the metal was changing the nature of the carbon. And there was some historical evidence for this going back into the late 1890s with a different French chemist named Barbier, who had studied similar kinds of reactions involving zinc rather than magnesium. They work in the exact same way. So what he did was mix these two species together on their own. So still magnesium metal, so I'm going to write that 0 again. And what he found was that the iodomethane disappears, right? And it took quite a long time for us as chemists to actually understand what's happening here, but now what we actually know occurs is a new kind of a step that we've never seen before in our class called an oxidative insertion, right? So basically what we're going to do is, well, I guess oxidize something, which we know is the magnesium, right? And it's going to insert, but it's going to insert into the Ci bond, right? So basically the magnesium is going to be like, don't mind if I do, and step between the iodine and the carbon. So we'd end up with a structure that looks like there is a magnesium iodine bond as well as a magnesium carbon bond, right? Okay, so if I look at what's going on here, again, from an oxidation state perspective, magnesium plus 0, but in the final materials here, this magnesium is actually plus 2. So in this oxidative insertion, the magnesium is being oxidized, right? If you like, you can think about it as the magnesium acting as a nucleophile toward this carbon. I don't necessarily think that's a great analogy because we actually know a lot mechanistically about how this works. I'm not going to go down that rabbit hole because it's complex to say the least, and it's something we don't need to be worried about right now. But I also want to focus on this kind of a compound where we have a carbon-magnesium bond, okay? So this is going to be the first instance of a molecule, of a kind of molecule that we'll see a lot and that are very important. These are called organometallic compounds because they have an organic piece bonded to a metal. Right, so we've got our organometallic compound, and then the last thing I want to do is to try this all together back to this observation that this carbon must have been nucleophilic in this reaction, right? So I want to actually focus on the nature of this carbon-magnesium bond, yeah? So go ahead and pause your video, and what I want you to do is look up the electronegativity of magnesium, right? Once you've done that, I want you to decide how this carbon-magnesium bond is polarized. Is there a dipole? Which direction does it point? And if you like, you can also write like partial charges, like delta minus and delta plus, to describe what's going on with the carbon-magnesium bond. I'll wait here while you look up the electronegativity of magnesium. All right, so you've looked up the electronegativity of magnesium, which you probably found to be shockingly low. So our magnesium electronegativity is equal to 1.3, whereas that for carbon, which you may have looked up or maybe have some general sense for, is 2.5. So this is a highly, highly polarized bond, and since carbon is actually more electronegative than magnesium, we're basically describing a situation where there's a significant negative charge buildup on the carbon while there's a positive charge buildup on the magnesium, right? And that's actually part of how we can justify this +2 oxidation level of the metal itself, right? So if this is what we're saying, that our carbon is actually highly negatively charged or partially negatively charged, then this carbon should be nucleophilic. So this is the exact argument we made when we were discussing borohydride or lithium aluminum hydride, that attaching these groups to a metal that's less electronegative than the element we'd like to make nucleophilic allows us to do that, right? So these organometallic compounds are very useful for this. We can actually take elements like hydrogen, or in this case carbon, and make them good nucleophiles by bonding them to the metal, right? So this will be the end of our first video for SLO6. We've discovered the Grignard reaction alongside Francois, right? We're seeing that we're forming carbon-carbon bonds where carbonyl carbons are, right? We're seeing that we can make carbon nucleophilic through the introduction of magnesium, and that involves halogens bonded to the carbons.